If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, welcome to another edition of Easy Theory. So today we're going to talk about this thing called the master theorem. And I put this in quotes because I don't actually think that's the best term for it, but that's what everyone else calls it, so I'm going to call it master theorem. All right, so we have talked about a lot of recursive algorithms, such as quicksort and merge sort and towers of Hanoi and other things. So we introduced this function called t of n, which is the runtime of the function. So in the case of, let's just say, quicksort, assuming we had a good pivot, we would get a runtime something like 2 subproblems of size n over 2, roughly, plus a big O of n to combine the subproblems. And we had something kind of like this for the Towers of Hanoi problem. So I want to generalize this, or at least the master theorem generalizes this to say, what is the runtime of a recursive algorithm that has some number of subproblems, let's call it A, and it's A subproblems, and each one of them is shrinking by a factor of what is called B. So before, this 2 on the bottom is not the same as this 2, but this 2 on the bottom here is saying the subproblems are half the original size. I'm assuming here that that B and A could be totally different. So maybe we could have 5 subproblems, and each one of them is only a third of the size instead of the fifth the size. And there are algorithms that have them be different here, so I'm allowing them to be different. By looking at this in a general way, we can answer any possible function that fits into this paradigm. Okay, so we have A subproblems. I'll actually write it out here. So this is the number of subproblems. And the B right here is how much smaller the subproblems are compared to the original one. So, and then, of course, what is the time to actually combine the 2 solutions together? Well, let's just generalize that too by saying we're going to have a function I'm going to call f to be the amount of time to combine the 2 subproblems. So this could be a wildly crazy function or just O of n or something. But this is the time to combine solutions, whatever that is. Again, we're making this as general as possible so that we could try to develop a general paradigm for it. Okay, so let's actually try to think about what is the runtime of an algorithm that behaves like this. Okay, and of course, you can envision that there are multiple t's in here, but here we're saying there's only one t. So all of the subproblems have exactly the same size, okay? I could have, say in the case of the Fibonacci numbers, where we had t of n minus 1 plus t of n minus 2, those subproblems aren't exactly the same size, fair enough? So here we're saying they're exactly the same size, and we have a certain number of them by indicating that here. Okay, so how would we actually visualize the algorithm running? Well, the way that we usually do this is with something called a computation tree. I know some other authors use different names, but this is what the name I'm using because it's my video. All right, so here's how we actually visualize this. Well, if I have just the original problem by itself, no recursion at all, then we know that the time to combine the solutions is not dependent on this anymore. It's only dependent on this. So the time to combine all the solutions in here is f of n. So assuming that there's no, we're done with recursive calls. There's no recursive calls anymore. But now let's look at when we do have recursive calls. So again, we have how many recursive calls? Well, according to this, we have a recursive call. So in the merge sort and quicksort algorithms, this was 2 because we had 2 recursive calls. So here we have a recursive calls. So a recursive calls. And we know that the size of each one of these is going to be n over b, because we assumed that all of the subproblems had exactly the same size, which is n over b. So each one of these has, is n over b in size, and I'm not going to write them all, n over b. So then the amount of time to combine solutions is, I'm going to use a different color for this, is f of that, because that's the size of that particular problem, and to combine all of its recursive call solutions, combining its ones, not all of these, all of the ones underneath this node right here, that takes f of the size of the subproblem time, which is n over b. So all of these, because they're all uniformly the same, are all going to get an f of n over b factor for each one of them. But across all of them, because there are a recursive calls, then what we can see is if we just add them all up, if we just keep a total over here, we had f of n over here before, and actually I'll move the total word up here. So total is right here. So total for the first row was f of n, but the total for the second row is going to be a times f of n over b, because each recursive call was f of n over b, and we have a of them. Fair enough. So then let's look at this one level deeper. So each one of these is going to get a recursive calls. I'm not going to add all of them, but yeah, so each one of these has a recursive calls. Let's examine one of them. Well, the size of this subproblem is 1/8 of this one, whatever it was, which is going to now be n over b squared. That's the size of the subproblem, and the time to combine all of its solutions is f of n over b squared. But now, what are the number of subproblems across all of these? There are going to be a squared of them, because we had a before, and each one of them has a of them now. So remember, there are uniformly n over b subproblems, and there are a of them. So the size is n over b, and there are a of them. So across all of them, we have a squared subproblems of this time to combine all the solutions. So the total for this row is going to be a squared times f of n over b squared. Okay. Well, how far does this tree actually go down? So yeah, so that's the question we want to answer. So how far does this tree go down? Well, it's got to stop at some point. Well, clearly, if we had a problem of size 1, then that's going to be a constant amount of work. So at some level k, well, when n over b to the k, because the two here are saying which level we're on, so the next level is going to be a cubed times f of n over b cubed. Next one's going to be 4's there, 5's there, and just keep going down. So at some level k, this fraction is going to be 1, and that's going to be constant work. So eventually we're going to have a lot of gigantic number of subproblems here. And if we examine one of them, so let's say that this is level k, and let's say that this is the bottom of the tree. So let me write that here. So bottom of the tree. So there are no more recursive calls at all, because it's a recursive algorithm. It's got to stop at some point, going down, I mean. So let's see. Well, how many nodes are at this tree? Well, since it's level k, the number of nodes is a to the k, because we had a fact multiplied at every single level. That's the number of nodes, and the time per subproblem, or to combine the solutions here, is going to be constant time. Why? Because it's at the bottom of the tree, and we typically will assign a constant amount of time for the bottom of the tree. So then that means that, well, what we have here is that f of n over b to the k, because that's the size of each of the subproblems, is the same thing as f of O of 1. Okay, so it may not take exactly one step, or whatever we want to. Actually, I should say it this way. Let's just say that the time to complete one subproblem is big O of 1. It might not take exactly one step. It may take a constant number of steps, but it's just some constant, because the size of the subproblem is only 1. So here, what we're going to say is that n over b to the k is going to be 1. We're just going to assign it to be 1. And then if we solve for k, if you remember your logs, this is the same thing as saying that k is going to be log base b of n. Okay? So log base b of n is the depth of the tree. Okay? So what will we actually need to do here? So what we want to do is to use this fact to try to determine the runtime of the algorithm. Okay, well, let's see. Let's actually try to heuristically figure out what's going to happen, though. Let's suppose that f of n right here is going to grow really, really, really fast. It's f of n is going to grow really fast compared to n. So then that means that what is the total runtime? The total runtime is dominated by the size of the bottom of the tree, because the number of subproblems is dominated by how many there are. There are quite a few down here. So it's a to the k of them. And if the total amount of work across each of the levels is continuing to go up, then it turns out we'll need to look at only the last row, and we'll see why that is. But if the amount of work that we're getting at each level is going down over time, so as we go down in the levels, the total amount of work that we do is going down, then you can actually show that f of n is going to dominate the runtime, which is at the top level. So there's kind of a balancing act here, that if we look at the total runtime and it's about the same at each of the levels, then we can actually figure out the runtime to be, it's basically, if it's the same at each level, then the total runtime across all levels is the time for one level times the number of levels. Okay, so let's try to heuristically figure out what's going on. So let's actually figure this out. So so let's examine the total runtime per level across all the levels. So let's see. So there are three cases in some sense. What's going to happen? Let me make sure this is on screen. Yeah. So there are three types of what can happen. So if the total runtime increases by a constant amount per level, then what we can figure out is the the total runtime, I should say that this total runtime right here is per level. Okay, so the total runtime per level increased by a constant amount, then the total runtime for the entire tree is dominated by the last level. And why is that the case? It's basically just a geometric series. So if you have something like 1 plus r squared plus dot 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 plus r to the n, and we say that r is bigger than 1, strictly bigger than 1, then each one of these terms is going to be a constant factor bigger than the other one. So then this r to the n, it turns out, if you can figure it out formally, this r to the n is going to dominate over all of the other ones. And the runtime is going to be big O of r to the n. So the runtime here, actually I already said runtime twice. So the runtime in this case is going to be big O of f of n. Actually, no, that's not right. Let's see, do I have that right? No, I have that wrong, sorry. So the runtime at the bottom is what's dominating here. So the bottom of the tree, which is the number of nodes at the bottom, that's what's dominating the runtime in this case. So what is the number of nodes at the bottom? Well, it's a to the k. Well, what could we actually do here? Well, let's see. Well, here we have that the number of levels is k. Sorry, the depth of this particular level is k, which is at level log base b of n. So what we can actually figure out here is that the total runtime across all the nodes, across the entire tree, is going to be n to the power log base b of a. And why is that? Well, this is basically just talking about the geometric series. Okay, and I'll leave you to actually derive why that is in the comments. But yeah, so the runtime here is basically the total number of nodes across the entire tree, which is approximately this amount. And I put a big O here because there may be a variability in the constant, but it's just a variability in the constant and nothing else. Okay, so what about in the case of where the total runtime per level decreases by a constant amount per level? Then what we can see here is we're going to have something like a geometric series again, 1 plus r squared plus dot 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 plus r to the n, but now, not n, r is strictly less than 1. And what you can show with the geometric series is that this converges to a constant. Okay, so this converges to a constant. And so therefore the total runtime across the entire tree is going to be a constant times whatever it cost at the top level. This converges to some number. So that's just some multiple of 1. And at the top of the tree, what we had was f of n. That's the time to combine all the subproblems. So the total runtime is going to be a constant times f of n. So the total runtime is going to be big O of f of n. Okay, cool. So that's the runtime if the total runtime decreases by a constant amount per level. But of course, the final case is where the total runtime per level is the same. If it goes up or down by an additive amount, like I add 5 or whatever to it, that's not going to matter. Here we're saying in these two cases that it increases or decreases by a multiplicative constant. So if I multiply by 2 or whatever. Here, this is saying that the order of them is the same. So they're big theta of each other. They're exactly the same asymptotically. They may differ in the additive amount, but not in the multiplicative amount. So what we notice here is that the level is the same. So then what we can infer is that the total runtime across the entire tree is going to be the number of levels times the total runtime per level. And what you can actually figure out here is that the total runtime per level, well, the first level is f of n. So all the levels are about f of n approximately. And the total number of levels is log base, so what did we figure out? It was a log base b of n. Well, b is just a number. So we can factor that out of the runtime here. I mean, the big O notation. So the correct answer here is actually big O of f of n times a log base b of n. But I could eliminate that b here because the b is just a constant, and log base b of something is dividing by log b, assuming that you standardize the bases in the logs. It's not important. The important thing is that the runtime is the number of levels times the cost per level. And so those are the three possibilities. So all algorithms that behave according to that recursive definition that we had, that have all recursive sizes exactly the same, and a certain number of them with a function to combine all the solutions, every single algorithm is either going to have this runtime, or this runtime, or this runtime. Every single one, which is pretty cool. So hopefully that was interesting. Leave your comments down below for anything interesting about the master theorem. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, I'll see you next time.